Okay, hello everyone. Today we're going to go over Fall 23. I'm just going to go problem by problem. So I'm starting with the reminders long answer. So let's go through this. Okay, so we're building some interactive productivity tool in Pintos. And we see with this example that we are printing reminders at set intervals, and a user will specify the message and the time interval at which that message should be printed. So in this case, if a user schedules a help reminder with interval 10, starting at time 100, we should see help printed out at time 110, 120, 130, etc. So if we look at the functions and syscalls that we have to use for this program, we see time will give us the current time in seconds, and sleep is going to put the current thread to sleep for the specified number of seconds that you pass in. And just a note about the size of the strings, you can assume all of the strings are under 100 characters. We'll kind of table that for now. And the last few functions that we see, so we have this function get user input that is just going to return the input string from the user. And if there's no input ready, it will put the calling thread to sleep until input is available. So just kind of a walkthrough of the problem, and we see in this main thread, we're going to call get user input and then do something that processes the user input. Again, we remember when we're calling get user input, if there's no input ready, putting the calling thread to sleep until there is input. Okay, so the first question, Sahya intends to implement the reminder tracking and printing logic on the main thread in the process user input section. So this question is saying that Sahya is planning to do this reminder logic of iteratively scheduling reminders to be printed at a certain interval in here. And so what is a potential issue with that? Well, we said that get user input is going to block until user input is available. So if we already have a reminder, like this help message, that we want to schedule at certain intervals, and we then try to get some user input, our main thread is going to sleep when maybe during the time it's asleep and waiting for another user input, it should actually be printing out reminders from the previous. Okay, hopefully that makes sense. Now we're going to go to more of the coding questions. So let's take a look at what we're given in the code base. We have this struct reminder that's given, or that has a string for the message, or a string pointer, char pointer for the reminder message. We also have the interval at which we want to schedule the message. And then we add a variable called target time for when the reminder should be sent next. So for example, if we go back to the example we're given in the problem, if we schedule a reminder named help with interval 10, this reminder struct is going to look like help, and then the interval will be 10, and then the target time initially is going to be something like 110, right? Because we schedule it starting at time 100, and we want to print out that message every 10 increments, or 10 seconds. Yeah. So then we have a list of reminders. So remember, we can have multiple reminders. There might be help, there might be hello world. Those are kind of odd examples of reminders, but anyways, you can have multiple reminders that you want to set at different intervals. And so we have a list, a corresponding lock that we'll see how we can use, and then we also have a condition variable. And we'll also kind of table that for now and see how we can use the condition variable later. And so in our main function, we're going to initialize this list of reminders, and we actually implement to initialize in the next page. And then we create a thread that's just going to run this function runner, which takes the list of reminders and is going to do the logic that we specified previously, where it's printing out reminders at their set intervals. And so keep in mind, again, we can have multiple reminders at different intervals. So we're going to implement some complex logic for that. Okay. So now as another primer, I mentioned we can have multiple reminders. And in this example, we have 2 reminders that we set: work on design and stay focused. Okay, so starting at time 0, we schedule this reminder. And because the interval is 15, we're going to print out work on design at time step 15. So that's going to be our first output. And now at time step 20, or also, I guess, we now note that after we print out work on design the first time, it's going to be scheduled next to print out at time 30, time step 30. Okay, before that happens, so before the second time we print out work on design, we add another reminder that says stay focused, and that's going to be printed every 5 seconds. So that means at time step 25, we print out stay focused. And what happens next? So at time step 30, we have 2 reminders that are scheduled, right? So we have work on design, and out of laziness, I'm just gonna okay, so we have 2 reminders that are printed at time step 30. I guess this actually says specify the time before the message, but same answer. And before either of these reminders gets scheduled again, at time step 30, we exit all threads, or we exit the process and we kill all threads. So nothing is going to be printed after that. Okay, so that's kind of a primer. And now we're actually going to write some C code. So we need to initialize our reminders list with this initialize function. And if we see in this struct, we have 3 attributes. So we have a list, a lock, and a cond. And any synchronization variable that you're using, you're going to have some init function. So we definitely need to initialize both the lock and the condition variable. And likewise for Pintos lists, you always need to call list init. So this is pretty easy. You're just going to call the corresponding init functions. So I'm going to write out some pseudocode for the sake of time. So list init at reminders, I'm just going to call it rem for now. And then I have lock init. And just make sure for any list init, lock init, and con init function, and I guess some for semaphores as well, you're going to typically pass in the address of the list or lock or whatever you're initializing. And that's pretty standard. I have a longer ed discussion on that if you're curious. So feel free to ask me about that. Okay. So up till now, nothing too crazy, but now we are going to actually get into the reminder logic, which is a lot more detailed. So okay, I'm back. So now we need to implement add reminder, which is going to add a new reminder struct into our reminders list and then signal the condition variable. We'll break down what all of this means in a bit. But to start off with part A, we need to initialize the reminder somewhere in memory. Now this gives you some indication, or typically we consider should a variable be initialized on the stack or the heap. If that variable is only needed for the given function, you can typically initialize it on the stack. But in this case, you want this reminder struct to persist because it's going to be added to the reminders list and you're going to need to use it later on. So allocating it on the stack would be pretty bad, and it would basically be erased after the function terminates. So erased really meaning any local variables allocated on the stack for a specific function are deallocated when that function exits. So we're going to allocate reminder on the heap. The way we do that is with a call to malloc, and we're just going to pass in the size of the struct. So size of reminder t. And yeah. Okay, so now we see that reminder has 3 attributes. And so that gives us some indication. We see here B is 3 lines, and there are 3 attributes of a reminder struct that we need to fill out. There's the message, the interval, and the target time. This is a lot of writing. Sorry, my handwriting is kind of a mess, but yeah. So starting with the interval, that's pretty clear. It's given to the interval variable here is parameter, I guess, is already specified. So we just set it to interval. And then our target time. So if we look at the example where at time 100, we schedule help with an increment of 10, we know that the target time in this case would be 110, meaning at a time equals 110 seconds, we want to print out help. So we're going to add the current time to the interval. And we remember that time was already specified to us as a syscall that gives us the current time in seconds. And then for message, in the problem description, it's specified that message is not going to persist beyond this function call, or that you may not assume that it will persist, which gives you some indication that you should copy over the message parameter somewhere in memory that's safe. And so with a similar concept, you don't want to, or a similar concept to what we discussed before, you don't want to copy that over onto the stack. So instead you can use stirdup, which is going to malloc some space for the string and then have call stir copy to copy over whatever you pass in to the newly allocated space on the heap. And yeah, so this is going to take care of copying over the message parameter that's passed in to a more persisting location on the heap so that the reminder struct can access it later on. Okay, moving on. So we've basically initialized all we need for reminder. And now what else do we need to do? So we remember that we're given 3 parameters. We already used message, we used interval. What do we need to do once we actually initialize a reminder struct? Well, we have a list of reminders, so we're going to need to add the new reminder to that list. And to do that, at some point, we need a call to list pushback where we pass in the address of the list. And then the list lm of whatever struct we want to pass into the list or push to the list. Yeah, so we need to do this at some point. And we also consider, are there any race conditions to pushing to this list? What if we're trying to add 2 reminders and we have 2 calls to add a reminder that may be interleaved? Is that possible? Well, we'll see if that is possible later on. But we also remember that our reminders list gives us a lock. And so that gives us some hint that we should protect something related to the reminders list. In this case, if we assume that multiple threads can try and add a reminder, then we would want to protect pushing to our list with some type of synchronization. And we also note that we have this call to con signal. And anytime you have a call to con signal or con broadcast or con wait, so anytime you're using a function related to a condition variable, you need to first acquire the lock so that you can pass in, or so that if you're calling con wait, you are going to atomically release the lock. Keyword, you're releasing it, so it had to be previously acquired before you actually call con wait. And then similar with con signal, it needs to know what lock corresponds to that condition variable. So, okay, that gives us the answer that we're going to acquire the lock here. Okay, this is kind of writing over. Then we always, when we acquire a lock, we need to release it at some point. So we can release it after we call con signal. And this is like a very standard implementation of a condition variable where you acquire the lock. Maybe you have some logic before you call con signal, and after you call con signal, you can release the lock. Yeah. And just a reminder for mesosemantics, when you call con signal, it does not automatically give up the CPU and the lock to another thread. Instead, it signals a waiter or like a waiting thread and puts that thread on the ready queue so that it can run later after the lock has been released. And then the thread that actually called con signal is going to proceed, eventually release the lock, and the waiting thread that was put on the ready queue can now reacquire the lock from a call to con wait and continue executing what logic it had after that con wait. Okay, so yeah, I think I'm going to write very quickly. So this doesn't look great. But okay. Okay, so we implemented add reminder. Now let's look at our next function, which is wake after delay. So the problem doesn't give us that too much, but it says that the function or wake after delay should sleep until the target wait time has been achieved, and then it should signal the condition variable. Okay. So starting off, we see that we have a new struct here called delay info. It's going to have some condition variable and a lock again. And note that unlike in reminder list, where we actually have the lock and condition variable itself, not just pointers, here we actually have pointers to the condition variable and the lock. So kind of a hint, like again, here the condition variable and lock are actually allocated in the struct reminder list itself. Here in delay info, they're just pointers. And we'll keep that in mind. And then there's also a target wait time in our delay info, and we'll see how that works later on. Okay, so when a wake after delay thread, or when we run wake after delay, we're given an info or a delay info arg, and we note that there is already a target wait time here. So if we're trying to calculate the time until we should wake up, we can subtract the target wait time or wake time, sorry. And the current time. And so for an example, if like the target wake time from our previous example with help, that's called at time 100 with an increment of 10. Here, the first target wake time is 110. And if the current time is 105, we know that we have 5 more seconds to wait. Okay. Yeah, so the way I kind of describes my approach to A is more intuitive based on the names of the variables. And I think that's easy when you don't yet have like a big picture of the problem. But okay, so now we see we have an if condition, and if we enter that, we put the thread to sleep for the specified number of seconds that we just found. And we consider when would we want to put the thread to sleep. Well, if we still have some time to wait, we want to go to sleep until we should be woken up, right? So if I have 5 more seconds in this case until I want to print help, I should go to sleep for 5 more seconds. When should we not sleep? Well, if time till wait is less than or equal to 0, so if I'm already at time step 110, I do need to print my my message. So I don't want to sleep in that case. And so that gives us a solution that if time till wake is greater than 0, we are going to sleep the specified amount of seconds. Okay, so now we have another condition variable pattern. And again, anytime you see this const signal, we know that we need to first acquire a lock and then release the same lock. And in this problem, it's pretty clear cut. We only have one condition variable and lock that we're using. And so we're going to acquire the lock, or I guess we technically have 2, one that's declared in a reminder list and one that's shown here, but we'll see how they're related in a second. So just based on inference, if I have a const signal and my only argument to this function is this delay info struct, I can kind of intuitively discern that I'm going to acquire the lock that's given in the argument. That's the only lock I have to work with here. And I'm going to release the same lock, and same with the condition variable. So I'm going to signal the cond in the wait, or sorry, the delay info struct, and I'm going to pass in the lock for that condition variable. And note what is different between this lock acquire and const signal versus this lock acquire, for example. Well, in one of them, we have an ampersand, and that's because lock acquire takes the pointer to the lock. Here, we're already given the pointer to the lock, right? This is not a struct lock, it's a lock pointer. So just like a small note, I know there's been like a lot of questions about when do you pass in the pointer versus the value for this type of thing. So yeah. Okay, so we basically walk through this function kind of just like with some intuition based on the arguments that were given, but to again step back and see what this function is doing. So we're given some delay info arg that is going to cause the thread to sleep if we need to wait some amount of time before printing the reminder. Once it wakes up, which means that it's ready to print the specified reminder, we're going to signal this condition variable, and the rest of the logic is going to be taken care of in runner. And I think the confusing part here is you don't see anything about the actual message, and we'll figure out why in the last part. Yeah. So I think the order of these functions can be a little bit confusing, but this one, even though you don't have that much information yet, is pretty intuitive based on the arguments. So if you're ever lost in the big picture, I would consider what do you actually have to work with, and based on the boilerplate code and the arguments that are passed in. Okay, so now we actually have our runner function that's going to implement the remind sending feature. And we have this clause that if n is the number of notifications, the number of while loop iterations must be at most twice as many notifications. We'll kind of table that for now and just think about what logic we need to implement. And so again, we see this pattern that we have a call to con wait. Every time we have con waits, we need to have a corresponding lock acquire. So that's going to hint that the first thing we do is we acquire the lock for that condition variable, and that's going to be the reminders lock. So I'm just gonna put it like here. And then what do? I get the current time. I have this target wait time variable that's temporarily set to maximum integer value. And we see the comment says this variable should correspond to the target time of the closest reminder. So to take a step back, runner has this list of reminders. And based on all of these reminders, we need to determine the earliest time that a reminder should be printed. Okay, now we have this for loop iteration that based on this line, you can also kind of infer how we need to iterate through reminders. We're also just on the basis of the problem that we need to find, this target time of the closest reminder, and that this runner function is responsible for actually printing out all of the reminders or setting up that logic. So we're going to use the Pintos list API. And first, I'm going to set a list lm pointer. Okay, this is going to overflow. But in B, I'm going to set this element E to the front of the list. So that's just going to get my first list element. And this is becoming super long. Okay. So I get the first element, that's the first part of my for loop. Then I think about when do I want to exit out of the for loop? Well, when I hit the end of the list. So I check that it's not list end. Okay, I'm just going to call reminders rem. So if you see rem, there's actually reminders. And how do I continue iterating in a Pintos list? I call E equals list next E. So that is going to grab the next list lm pointed to by our current element E. Okay, and so again, when we have some Pintos list iteration, we're iterating over list lm structs or list lm pointers. And list lm pointers, list lm structs are always contained in some parent struct, as I like to call it. So in this case, we have a reminder struct, and list lm is going to be embedded inside that reminder struct. And so to actually extract this entire reminder struct that I like to call the parent or like the container struct, you're going to use this macro called list entry. And list entry takes in 3 arguments. It takes in the list lm. So in this case, it's called E, or I called it E, call it whatever. It takes in the name of the parent struct, in this case, reminder T. And then it will also take in the name of the list lm that, as you declare it inside of struct reminder in its like declaration earlier, which is going to be lm. That was mildly coherent. So just going back to our declaration of the struct reminder, our list lm attribute is called lm. So that's what determines the 3rd argument in list entry. That can be kind of confusing sometimes. Okay, we went through this. Okay, so now we set up this iteration to go through our reminders list. We extracted the reminder struct corresponding to the current list lm. And now we need to check whether we should print the reminders message. So we have, what do we have to work with? We have this T variable that gives us the current time. Every reminder has an interval time. If we go back to this, and it also has a target time. And so assuming target time is already set up for us, we can just check if the target time is less than or equal to the current time, we can print that message. And intuitively what that means, if let's say the target time is, this is not the right, less than or equal to T, which is our current time variable. So intuitively, if our target time is 110, like we had in the previous problem, and our current is 110, we want to print our reminder message. If for whatever reason, this function was, or this line was not called for the specific reminder at exactly time 110, you still want to print the message. So that's why you have this less than or equals sign. Yeah. Okay. So after we print the message, this means again that if we take the example of hello 5, or I guess it was 10, right? So in the first time that we print out hello, it's printed out at time 110. The next time we print it, we want the current time to be 120, or we want to print it at or after 120 seconds. Yeah. So again, we know the target time based on the target time attribute of the struct reminder. And so once we printed the message for like one iteration or for one time step, we want to update our target time, right? Because after we print hello at time step 110, we want to then print it at time step 120. So your target time inside of the reminder struct is going to change. And so we're going to, after we print out the reminder message, we want to increase the target time of that reminder by its interval. And that's where we get, trying to see where to write this to make sense. Yeah, I'll write it like over here. So that's where we get this reminder target time plus equals its interval. Again, I'm just referring to reminder as rem. And now we have another if statement. If something, we're going to update our target wait time, not to be confused with this variable. We're going to update our target wait time that we declared over here. Let me use a different color. To the reminder's target time. And so if we consider again what this variable represents, we want to find the closest reminder that should be printed. So if we have like a bunch of reminders, I'll do like R1, R2, R3, and this should be printed at time 110, this at time 105, and this at 102. We want to wake up in time to print reminder 3 because that's the earliest reminder that needs to be printed. If we only wake up at time like 110, we've already missed both of these reminders. So that's why we have this variable to that we're later going to use to know when to wake up again to print the next reminder. And so we want to take the minimum target time across all reminders. So we're just going to check if the reminder's target time is less than our current minimum. Oh, that's not how we're going to change that, update this variable to refer to the new min. And we also see target wait time is actually used over here in a delay info struct. And if we remember from the previous part, we use a delay info struct in this wake after delay function, which is going to sleep for some amount of time until we need to print the next reminder. So that gives us some more intuition of how runner and wait for delay are related. And I had another note, but yeah. So to go quickly over I, and then we'll take like a bigger step back and look at the big picture of these functions. We see we have some delay info argument, and we want to allocate it somewhere in memory. And so we're going to call malloc for similar reasons that we previously discussed. Pass in the size of that struct, so size of delay info t. Sorry, this writing is such a mess. And now J is a little bit less obvious, I would say. But we can take a step back and now see, despite this horrendous writing, runner is going to continuously iterate through all of the reminders, print any reminders that need to be printed based on the current time step, update any target times for messages that have been printed, and based on those updated times, going to find the next time that we should wake up to print a message or a reminder message. And the way that we actually sleep until we need to wake up and print the next reminder message is based on this wake after delay function that we implemented previously. That is going to sleep for some specified amount of time and then signal this condition variable that it is waiting in runner. So that means that we want a thread to run wake after delay. And so we're going to actually create a thread in J. I'm just going to pretend this is J for a second so I don't have to flip the page. And I'm going to create a thread. You don't need to store the create a thread information. You just need to run it. That runs wake after delay. And that takes in this info struct that I previously allocated with the condition variable and lock for the reminders list. And so this is what I alluded to before, where we noticed that in the delay info struct declaration, we have a pointer to a condition variable and a lock. And in the reminder list, we have we allocate space for the condition variable and the lock itself. And so the condition variable and lock that you're actually using for the delay info struct is just a pointer to the condition variable and lock for your reminders list. That was kind of a handful to say, but hopefully that made sense. Okay, so yeah, one more time, you are creating a thread that is just going to keep running and running. That does the following. First, it's going to wait for some specified amount of time. When does this get signaled? Well, it gets signaled in wake after delay when we no longer need to sleep, or more so, a message needs to be printed. And so wake after delay is going to, there we go, signal this condition variable that is being waited on here. So once our program is ready to print out a message, con wait is going to be signaled from wake after delay. Runner is going to wake up and then do the rest of the logic. And again, just a note, right? So with condition variables, because I know some discussions didn't get to cover this, you first acquire a lock that's associated with that condition variable. And when you call con wait, it's going to atomically release the lock and put the thread to sleep. And whoever signals that condition variable is going to wake up the next waiter. If we use con signal, if we use con broadcast, we're going to wake up all waiters. And wake up just means that we put them on the ready queue. It doesn't mean that we run all of the threads or we run the specific waiter right away. In mesa semantics, we actually don't necessarily run the waiter we wake up right away, but we just put them on the ready queue. And in horse semantics, you actually, when you call consignal, you give the lock and the CPU immediately to the first waiter. And so you actually do have a guarantee that there's a more, I guess, defined connection of when the waiter wakes up and how the lock is given to the waiter. But yeah, in mesa semantics, it's what we said before. So just keep that in mind. And that was about condition variables. So once we are signaled, we know that we need to print out some message. We iterate through all of the reminders, see what messages we need to print out. print them out if we need to. If we printed out a message, it means that we need to update its target time to the next iteration that it should be printed out. So we do that in step G. And then we have a variable that takes the min of all of these target times called target wait time. And we pass that into a wake after delay thread that's going to wait the minimum amount of time it needs to print out a reminder before waking up runner again. So we have this relationship between runner and wake up after delay, where every time we execute an iteration of this while loop, we're going to create a thread that runs wake after delay, sleeps for a bit, and in that time, runner is blocked because cond wait is going to be, or it's going to be blocked on cond wait until someone signals it. So in wake after delay, we're going to sleep for some time and then signal that condition variable. Runner is going to re-wake up after that cond wait call and execute another iteration, check who we need to print, and keep iteratively doing that until the program terminates. So yeah, hopefully that made sense. I know that's a handful. Let me know if you have any questions. And yeah, thanks guys.